Well, it's a pleasure to be with you tonight. And my name is Ken. I'm N7KM, probably the most ancient radio operator in the area. I got my first license when I was 13 years old. And that was back in 1956. So that gives you an idea of where we're at. And this is a great hobby. I'll tell you, it is a great hobby. I've been active in ham radio the whole time, all the way from then till now. That's some 65 years. And I've been involved in a lot of different parts of it. And to kind of let you know a little bit about what I do, I'm what's called a QRP fanatic. You know what QRP stands for? That means low power radio. And I have right here one of my complete low power radio systems. And I just wanted to run past you here. If you're going to go out with a radio, in fact, whether it's at home or wherever you happen to be, the most important part of it is the antenna. That's my antenna. And I have a little, you know what a potato cannon is? I go out in the mountains and I shoot a rope up over a tree, and then I pull the antenna up there and hook onto it. So I have the antenna, and then you have to have transmission line, and we're going to be talking about these tonight. And this is my transmission line, lightweight transmission line. This is very important. What's that? That's a Morse code key. And as I've already told you, I'm a Morse code nut. And I started off, when I first started off, I was so slow. I was a young kid. It was in Boy Scouts, and they were teaching us dits and daws, and then they taught us how to wave flags. Dit, daw, you, and then go on, and we'd copy messages across the canyons. And then when I was in junior high school, I had an electricity class, and the fellow that was teaching didn't know anything about electricity. But he said, to keep our interest, he said, well, maybe we could all get ham radio licenses. And so we started studying, and you had to be able to send and receive Morse code at 5 words a minute to get that license. And then that led on and on and on. I went in the military, and as a ham radio operator, I'd been operating. I got back at Fort Gordon, Georgia. This is just right at the beginning of the Vietnam War time. And I was at the radio school at Fort Gordon, Georgia. And this old sergeant, I'm trying to remember if he was a sergeant major or what he was. But anyway, he came in and he sat down at the table and he sent Morse code because I was at a communications class. And he just wrapped it right off and he said, now I'm sure nobody got that because that's what you're striving to at the end of the class. And I raised my hand and he just looked at me and he said, ham? Yeah, I want to see you after class. So while all the other fellows were there with the headphones on and the radio pounding in on them, and the code for hours, they sent me off to advanced training classes and all these kinds of things, all because of my ham radio. But Hammer was the best code operator I've ever seen. He could send and receive. He could send a Morse code message with one hand, copy one over here with his other hand at the same time, and carry on a conversation. I never have seen it. I can send and receive with one hand and talk to somebody while I'm doing it, but I could never do what he did. It was absolutely amazing. So anyway, Morse code is what I use when I go out on the mountaintops. This is my power supply right here. That's what I carry out to power it with right there. Did you ever see one of those? Okay, that's the power, and when I want to operate a little longer, this is the bigger one. It keeps me going for longer. So that's the power supply, and this is the radio. And this is a complete 3-band radio. and that's the radio. And in here, I also have a little pair of headphones and a little connector to connect it to battery. That's all you need. And then I have, of course, a logbook. Now, about a year and a half, 2 years ago, I had just got this little jewel. And I wanted to put it on the air, so I threw my little antenna up in a tree, hooked the feed line onto it, and talked to a couple of guys around the United States. And then I heard this signal, pretty good signal coming in, and it was a station, an EA8 out of the Canary Islands, just off the coast of Africa. And this was my power supply. This was my radio. And it was very similar situation to taking a mini mag flashlight, turning it on, pointing it up over the North Pole and having somebody hear it over in Russia. That's the kind of thing, or see it, okay? And I thought, I wonder if he could hear me. And people were calling him, and all of a sudden there was a little break, and so I just stuck in there, QRP, QRP, QRP. And all of a sudden he comes back and says, the QRP station. And I talked to him for just a couple of minutes there. But, you know, here I'd been a ham 63 years or something. And I've worked got all these awards, I've done all these, but my heart had never pounded more than when that guy came back to me with that little tiny radio right there. Now, the name of the game though, it doesn't take a lot. You can build a little radio very similar to that for about 55 bucks. Okay, this one's a little more, it's a little fancier. But if you know what you're doing, little antennas and so on and so forth, you can do big things. And tonight we're going to talk about antennas. And I always get to talk about the most interesting subject there is, okay? Because people have a tendency to put all their money into these great big radios when in reality they can put a few dollars into a good antenna and do more than the guys with the big $10,000, $12,000 radios. Okay, so we're going to talk about antennas. So this is me. I'm going to keep it very simple, non-mathematical, but next slide, please. Your enjoyment in amateur radio will increase as you come to know how things work. You come to know how things work. For instance, he's talking about radio. It's interesting. You can walk into and listen to a receiver and you can tell whether the station's way away or anything else because you understand how everything works, just the way things sound. It's exciting. So when you push the microphone button, if you know what happens, or if you push the key and you visualize in your head what happens, for instance, it's exciting to be able to hit the keys on a computer and think about, know everything that's going on inside there before it comes back up on the screen here. That's exciting. And people who just buy a radio, hook it up and talk on it, don't even know how it works. They don't really get excited until they start to understand. So tonight we're going to discuss about antennas. That's a very complex thing. I have taught communications engineering. I've taught antenna systems, mathematically the whole thing, but tonight we're going to use the thing that says KISS. What's that? Keep it simple, stupid, okay? So except that we're not going to use the second S. We're just going to keep it simple, okay? And next slide, please. The antennas that we're going to be talking about are basically the ones that you're going to be asked questions about on your test. And they're very simple antennas. They're very inexpensive. This little antenna right here, for instance, you can go online, buy them, and so on and so forth. They'll cost you not too bad, you know, 70, 80 bucks. Or you can build it. I think this one cost me, I don't know, $7 or $8 maybe. Something like that was for the box to put the toroid in. But antennas is fascinating because you can build them, you can play with them, you can do it very, very simply. Okay, next slide. Now, Have any of you heard the term transducer? Okay, what does the word transducer mean? Well, I asked Siri, and this is what Siri said, since she seems to be the expert, right? A transducer is a device that converts electrical energy from one form into another, okay? Usually a transducer converts a signal of some kind, one form to another. The act of doing that is called transduction, okay? Transduction. And the common ones that you're familiar with are your ear, your eyes, a microphone, you talk into it, it takes the mechanical wave, comes out of your mouth, converts it into an electrical wave that can be amplified, so on and so forth. That's a transducer. Well, an antenna is nothing more than a transducer. It simply takes electrical energy, converts it into a different back and forth between forms, okay? Next slide. An antenna then is a special kind of transducer. It converts alternating currents, voltages, magnetic fields into electrical currents and so on and so forth. And it also converts them into what is called a transverse electromagnetic wave. Whew, that's a big word, right? Transverse electromagnetic wave. Well, we said we were going to keep this simple, but before we get done with this, you'll understand exactly what that means, okay? Next slide. Okay, let's take a few minutes. We're going to talk about things you already know, okay? Things that you already know. Let's go on to the next one. We're going to tie. One thing that we're going to talk about is magnetic fields. Now, has everybody played with a magnet? You know they have two poles, right? They have fields that go around the outside, right? And the magnetic fields, you'll notice, flow from the North Pole to the South Pole. Okay? Everybody played with one of those? Okay, next slide. Okay. It's very interesting that electrical currents also have magnetic fields associated with them. For instance, if I take a piece of wire, we're not looking at the antenna now, just a piece of wire, and over here I have the positive of the battery, and over here I have the negative of the battery, the electrons will flow from the negative over to the positive, right? Well, whenever a current flows through a wire, it sets up magnetic fields around the wire. In fact, there's a rule, if you're talking electron flow, that says that if you wrap your hand around the wire with your thumb pointing the direction that the electric current is flowing, your fingers are wrapped the direction that the magnetic fields are going. Okay? Does that make sense? So if I switch the battery, I go like this, and what do the magnetic fields do? They're now going the other direction, right? Okay, next slide. Okay, it's an interesting thing how magnetic fields interact with wires and wires interact with magnetic fields. When magnetic fields are in motion cut across the wire, it produces voltage and current across the wire. When current flows through a wire, it produces magnetic fields around the wire. Next slide. Okay, right here. On the top, you see a magnet going in and out of a coil of wire. What do you notice about the meter? Okay, when it goes one way, the meter goes this way. When it goes the other way, the meter does what? Goes the other way, okay? And down on the bottom, I have a constant magnetic field, and I pull the wire through it. And what do you notice? When the wire comes down through it, what happens? Current goes one way. When you pull it up through it, it goes the other way, right? Okay, so we see then that a magnetic field cutting across a wire produces current in the wire. that make sense? And when we have current flowing through a wire, what do we have around the wire? Magnetic fields, okay? And they exist at the same time. Next slide. Okay, if I take that magnet now and I make a loop of wire and I rotate the wire through the magnetic field, the wave that is produced is this wave over here. That's the voltage going up, the voltage coming down, so on. What's that called? Sine wave. Sine wave, right? Because you can graph the sine of the angle that thing's going through, and that tells you what the magnitude is. But what happens is that's the sine wave. Now, if I speed that wire up and make it go faster, what will happen to the sine wave? The shorter. If I slow it down, what happens? Longer, okay? In fact, one revolution here, right there, we see that's called 1 cycle or 1 hertz. It was named after Heinrich Hertz, so it's capitalized HZ, okay? And down on the bottom there, you see a big, powerful formula that says that 1 over the frequency equals the amount of time, and 1 over the time equals the frequency. For instance, if it takes 1/10 of a second for that thing to go around, what's its frequency? 10, right? Okay. Now, the only thing is that what we're talking about here is your radio transmitter, this little radio transmitter right here. When I touch the key on one of the radio bands, it makes a sine wave like that goes at 14,435 times a second. How long a time is that? Well, 1 over that, and you've got it, right? Okay, now, so that then is frequency and time. That's kind of the relationship. Does that make sense? And it all comes from a magnet and a piece of wire. Is that right? Is that tough to handle? Next slide. Okay, when we build an antenna, we are playing with this concept. Right here is one of my little QRP antennas. And I better not unwind the whole thing. Anyway, you can see up there on top, you'll notice it says that this antenna, in fact, on the bottom it says there, this antenna has a length of how much? A half a wavelength. A half a wavelength. Now, what's a wavelength? Okay, it relates to frequency. Does everybody know how fast the speed of light is? 186,000 miles per second, okay, or 300 million meters per second. Well, it turns out that the wavelength is the distance that a wave traveling at the speed of light travels during the time required for 1 cycle. Does that make sense? Okay, for instance, 2 meters, and you've heard the guys talking about that. 2 meters, where does that come from? Well, it turns out that 2 meters is about 150 million cycles per second, and in 150 millionth of a second, a radio wave will travel 2 meters. Does that make sense? No? No, but by the time we finish, it'll make sense to you. Okay, so that's called the wavelength. Okay, and these antennas we're going to find out are a half a wavelength long. Next slide. Okay, all a radio antenna is a device which you pump electrons back and forth across the wire like this. Okay, you just pump. Now, if you pump an electron across here, what happens around the wire? Magnetic field. And the top one right here is where it says VO, that's a transmitter. And the transmitter pumps the energy up, and when it pumps the energy up, it makes the radio wave, or the wave go back, the electrons go back and forth across the wire. Okay? Does that make sense? Yeah, same thing. Okay? So when you transmit, when you key the radio, you make the electrons go up and you pump them back and forth across this piece of wire, and that's called an antenna. Okay? And when you pump it back and forth across there, it sets up magnetic fields. But if we look at this, just for a second, to kind of clarify, if I have this, and that means that's an alternating current generator, right? Okay, and I bring it up here, and for right now, we'll run it through a resistor like that. Well, as I look at this wave, during this point in time, this is plus. So make this plus, that's minus. So the electrical current flows around like this, right? Then, when you get to this point, it stops again. It was 0, went to positive, then it goes negative. And when it goes negative, all of a sudden this becomes minus and that becomes plus. And what does it do? Now the current goes around the other direction, like this. Okay? And if I put a meter across that, I'll see the voltage on this go up, down, up, like that. And that's, okay? So, with this radio antenna that we're going to be talking about, I put the thing on here, the electrons run down here and they just get to the end, and all of a sudden it changes polarity. So all the magnetic fields have to go, okay? Then it does what? Goes the other direction, so all the magnetic fields have to do what? Expand out, okay? So that's the basic concept about an antenna. Next slide. And because of this, you see right up there, you can see the antenna and you see the energy, the electrons going, boom, chung, 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 right? And it collapses. When it goes again, you notice right there, all of a sudden, when the fields collapse, it leaves these magnetic fields floating off here in space with an associated electric field. Okay? Does that make any sense? Okay, so if that's floating out through space and I stick a piece of wire up here and that wave cuts across it, what happens in this wire? It starts oscillating, right? With voltages and current. That's an antenna. Next slide. Okay, when this happens, we end up with the voltages and currents across the wire. Now, if this was a resistor right here, and I assume that you've already talked about this, basic electricity, if we were talking about this, if this were simply a battery like that, if this was 10 volts right here, and this was 10 ohms, we could calculate how much current, because I is equal to E over R. So 10 divided by 10 is what? 1. Okay, so how much current flows through this thing? 1 amp. Okay? Now, the thing that happens with the resistor is, though, that this resistor right here gives off its energy in the form of heat. And if you reach over and touch it, you might get burned, because it's a transducer also, and it's taking the electrical energy and turning it into heat energy. Does that make sense? Okay, well, with this antenna, that's not what happens. We saw on the last slide, can you back that up? We saw on the last slide that when the fields collapse, Do all of them, does everything come back into the wire? No, it's radiated out through space, and that's what's called a transverse electromagnetic wave. It has voltage, it has current, and it's flowing out through space. And right now, the very fact that you can see me says you are seeing transverse electromagnetic waves, because light, radio waves, they are all exactly the same thing. And my image right here, the light coming off, bouncing off me, you have little things called rods and cones in your eyes, and there are little wires sticking out there. And they're at given wavelengths, unless you're like I am, I'm almost totally colorblind. You guys are all normal, I hope. But what happens is the light bounces off here, comes over, hits inside your eyes, causes little voltages in your eyes, and they're vibrating there. Your brain picks that up and says, aha, there's a person. He's wearing X color. He's got gray hair. He's got big belly. He's got all these things. Okay? But that's the way it works. Simply a transducer. You have them in your body. You're all around you. It's really cool. Okay. Now, on a radio antenna, as I say, you're going to have a transmitter, a box right here that's a transmitter. It goes through a feed line. That's the little wire that was going up the antenna. And then an insulator right here. The feed line is in two pieces. One's hooked to one side, one hooks to the other side. Now, it turns out that on a dipole antenna, and this is one of your questions, on a dipole antenna, you remember we did Ohm's law, right? Well, it turns out that if I look at this, the resistance of this antenna is 72 ohms. That's the resistance of a dipole radio antenna. The only thing is, does it give off the energy in the form of heat? No. Where's the energy going? Out into space. Okay? And so what we're seeing right there, if you were to measure the voltage and current right there and calculate it, you would say it's 72 ohms, but if you're putting 100 watts into that antenna, you're not sending 100 watts into heat. You're sending probably 90% of it out into space. Does that make sense? No. There are some things about you're on the right track, but we'll get to that. Okay. The antenna, you can't have a wire, an antenna made out of a size 64 wire and put 100 watts in there, because it'll melt down. Okay. But if you take a wire this size, that's number 12, maybe 14, you can put 100 watts on that really easily. Okay, next slide. Okay, so right there then we find that the impedance of a dipole antenna is what? It's called dipole because it takes two poles to hold it. No. Okay, it's running back and forth. It's how much? 72 ohms. That is a question that you're going to need to know the answer to. They'll ask you, what is the impedance of okay, now, it turns out that the dipole, which is this thing right here, insulator, wire, has a 72 ohm impedance. This antenna right here is what is called a vertical antenna, and it's only half as long here. However, the total length here is still half a wavelength. And it ends up, it would appear to be a 52 ohm resistor. And it turns out they make two kinds of coax. What are they? They make more. The ones that are used though is what? Okay, RG11 is 75 ohms. And RG58, so many others are 52 ohm. Why? Because there are two kinds of antennas. The one you put on your car is a 50 ohm vertical antenna. The one you hang up in the air is a 75 ohm antenna. And I don't have time to go through the math to show you why that's all so important. Okay, go. Next. Okay, now, very interesting thing right here, and this is also one of your questions, and it has to do with resonance. Resonance. So, we have the antenna, which is an insulator, a wire, a feed line coming down like this. The transmitter is pumping the energy into here. Now, this antenna here is at resonance. And what that means is the electrons leave here, they travel over to there, and they just get there, and what happens? Changes direction, so it comes back like this, right? Okay, when it gets over here, what happens? It changes direction. That is called a resonant antenna. What happens if I cut it off right there? Does it work? No. No, it's like taking a baseball. Here's an electron, you throw it at that wall over there, and it hits the wall before it's supposed to turn around. What does it do? Bounces back. That's called standing wave ratio, is the term that you're going to run into. Okay? Bounces back. What if the antenna is too long? It doesn't work. Okay? Now you see this little curve down here in the corner? That shows you the efficiency of the antenna. The very top point right there is the point at which the length is right and the electrons are going back and forth like this, okay? As I move away from that frequency, if I change the frequency of the transmitter, I start down the hill on the side. Why? Mismatch. It's no longer 72 ohms, no longer 50 ohms. Does that make sense? And what happens is, what's that? Yeah, what happens is, you can only use this thing to about this point right here. That's called the 3 dB point. And that says that when you shift off from the center, its efficiency will drop off and eventually you lose about half of your power because of the mismatch. Okay? And when we do that, we end up with what's called a standing wave. That means I send energy up to the antenna. The antenna doesn't want it. So what did you say? You said that it bounces back. So it bounces back. And when it comes back, we'll be under the transmitter down here if it's made to send the energy and it's getting both sending and receiving the same time, wrong phase. Okay? Okay. So do you understand what resonance is?
When you're tuning your radio, do you have to adjust your antenna?
That's right. You either, this antenna right here, by the way, this is an interesting antenna. My wife and I were living in New Zealand. And earlier Fred was talking about IRLP. And the guys back here in Cedar City, Utah, wanted to talk to me on the radio and do it well. And so one day we had a ham here in Cedar City. His name was Ken Oliver. And Ken, there was a little package showed up, a little tube, and inside the tube was this exact radio, this exact antenna. And he said, put a piece of string through here, hang it out on your garage, and then he told me what frequency to get on, and I already knew. And this exact radio right here, I was able to turn this radio on. It plugged into this antenna, transmitted over to another fellow's place there in Hawke's Bay, New Zealand. And I hit a couple things and a tone came up, and I was able to put in an IRLP number. That's a what? Internet Radio IR something project. Okay. Link project. So anyway, and then I put that number in, And then I waited, and all of a sudden a radio over here on this hill in Cedar City, Utah, I didn't get it. All of a sudden it tied that radio into the internet. The internet sent the wave clear over to Cedar City, Utah. It came up, went up to a radio repeater, turned the radio repeater on, and lo and behold, it says, "This is WR7AAA, Cedar City, Utah." And I said, "Well, this is N7KM in Hawke's Bay, New Zealand." And we just sit there and talk to each other. And it was this little antenna. Ken has since deceased and left us. What a great guy, though. And I keep this around just to remind me. And simple, is it expensive? No. Simple to build? Oh, yeah. I could have done it with a couple of coat hangers, but he knew me well, and he knew I wouldn't want to. I just appreciated what he did.
Well, copper would be better than gold.
Oh, yeah. Yeah, it would. Okay, next slide. So that's resonance. Okay, we talked about the power, and this is an example there. The dipole has an impedance of what? 72 ohms, okay? The coaxial manufacturer is 75. So if I have 75 ohms, 75 volts, that would give me 1 amp of current. And the antenna appears to have a resistance that's called its radiation resistance. And that's what it would be if it were dissipating power in the form of heat. Make sense? Okay, next slide. Okay, now, when we talk about antennas, we have this thing that we call gain. And everything that you do in life, you end up having some kind of a reference. Is that right? Okay, well, in antennas, you have a reference. This is that top thing you see up there. And this is called an isotropic radiator. And it is a mathematical figment of our imagination. It doesn't really exist. The closest thing I can think of that would be a isotropic radiator would be the sun. Why? Radiates in all directions. So this is the reference, and so this is called the 0 dB reference. Got it? Now, then on the bottom there, we have a dipole. Does it look like an isotropic radiator? No, why not? Well, there's the axis of the antenna, and it is transmitting a donut around the wire. And how much energy is out on the ends? None. So it turns out that this little basic dipole antenna there has what is called gain. It has 2.15 dB of gain. Okay? Now, when we talk about gain in antennas, if I can find my, right here, hold on to that for me, will you? Don't let the air out. Okay. Okay. I have here a light. Is it bright? Somewhat bright, right? Okay. I'm going to say that is the reference. Now I'm going to, is that bright? My question is the light bulb giving off any more light now than it did before? Well, why is it brighter? Because it is focused. Okay? So in ham radio or in any communications field, what you want to do is build antennas that have gain. And when it says gain, it means rather than having all of the energy going, you focus it down where you want to be. Now, Fred earlier was telling you about a little thing like this. This is called a Yagi Yuda. So except poor Yuda got left out. Two Japanese scientists one day had a couple of just these little dipoles that we've been talking about, the wire thing in the middle, and they had it on a receiver. And one day, Dr. Yuda or Dr. Yagi just happened to be walking by with another antenna, and all of a sudden they saw the meter on the thing go whoosh, whoosh. Do that again. She walks past. By golly, somehow or other we're canceling. Right here is the basic dipole antenna. Okay? When I pump energy back and forth across this antenna, it radiates it, right? Okay. Now, what if I was to place this at exactly the right distance? And so this one is putting the wave, is oscillating back and forth like this. The wave leaves here. When it hits this one, what does it cause it to do? Oscillate back and forth, right? Okay, well, what if I make this just the right distance so that the wave leaving this one and the wave leaving that one add together going that way? What did I just do? I just got gain. It's actually not double yet, but you got the idea, okay? Because this isn't 100% transfer. Now, on the other hand, I turn it around this way. Now, the wave leaving this one, it's going back and forth, hits this one. It causes it to oscillate, right? However, the wave generated by this one and the wave generated by this one are out of phase. What did I do with my, you may see what I did with my typical teacher. Okay, so in other words, one of them's putting out a wave that looks like this. And then we're imposing on top of it a wave that looks like this. What is the sum? If this, for instance, is plus 5 volts, and this is minus 5 volts, what does that add up to? 0. If this is then minus, that same situation. So what happens is these two waves cancel each other. Now, when I do that, this is called a reflector. And that says, for instance, we live very close to a place called California. Are there very many ham radio operators in California? No. Okay. You want to talk to somebody, California is right down there. You want to talk to somebody right up here in Michigan or somewhere. I'm turned around. Oh,
That way.
okay. That example. Okay. Okay, what happens is I have this antenna. Which way do I want to turn it? I want to turn it this way so that the energy allows me to talk to the person in Russia here. But what happens to a person trying to talk to me from California? They get blocked out. Okay? Now, if I want to talk to California, what do? Turn it around. However, off the ends out here, there's even less signal than there is from any of the other directions.
The difference is that one's closer.
It is a mathematical thing, and this is a poor example, by the way. It's a mathematical thing that allows you to spacing and phases. It is a real dandy math problem. Okay, but you get the concept. The idea is you have them add or you have them subtract. Make sense? Okay, we'll put this aside then. Okay, so what happens is then the reference antenna is the isotropic. The next reference that we quite often use is the dipole. And when you go out to buy an antenna, you have to know what you're doing, because they will say this antenna has 6 dB gain. What that means is if I put 1 watt in, the first 3 dB makes it equal to 2. The next 3 dB makes it equal to 4. Okay? Yeah. Okay. Now, when you buy an antenna, it will say 6 dBi, or in little tiny thing I, or it will say 6 dB little tiny d. Which one's the better antenna? Well, the D, the dipole already has 2.1 gain, dB of gain, right? How much gain does the I have? 0. So 6 dB above 2.15 is a heck of a lot better than 6 dB above 0. Does that make sense? So when you start buying antennas, you have to kind of know what you're playing with. Next slide. How are we doing on time? Oh, yeah. Okay, now, we said that the dipole antenna, if I have a dipole right here, waves going this way, it transmits this way, and it also transmits this way, right? But what about on the ends? None. This right here is a vertical. And this antenna, when I put it like this and I tilt these down at about 45 degrees like that, this antenna is 1/4 wavelength long here, and these are 1/4 wavelength. On your car, if you buy an antenna and you put it on top of your car, you have this sticking up, right? However, what is this? You don't see those on there. That's the metal in your car. So you put it on top of your roof or wherever, and then your car acts as the other 1/4 wavelength. Okay? Or if you better get a ham radio antenna, like I have one that I use on some low bands. The thing is about 60 feet tall. And my radials here, it is the ground, except I run wires out and bury it out there so that I can hide them from my wife. And it works. Now, this antenna, however, still has the donut going around here. So it sends and receives from all directions. And that's called an omnidirectional antenna. That's that one right there that you can see. Radio broadcast towers are generally vertically polarized. I mean, you talk about vertical and horizontal polarized too. Okay, and right there it shows it then 360 degrees. Since your broadcast stations that you listen to while you're driving down the road, their antennas are sticking up this way. By the way, let's just talk about that for a second. I want you to understand. The electric fields are always parallel to the wire. The magnetic fields are always perpendicular to the wire. What an antenna's polarization is determined by its relationship to the electric fields. So on this point, I have a plus here, a minus here, the electrons are running this way, right? So the electric fields are this way, therefore this is a vertical antenna. If I put it like this, now what is it? Horizontal antenna, because the electric fields are parallel to the Earth's surface. That is one of your questions. You need to know about polarization. So if it asks you about a dipole or something being hung in the air, and the wire is parallel to the Earth, so therefore what's its relationship? It is a horizontally polarized antenna because it's parallel to the horizon. Okay, next slide. Whoops, we just had that one. Okay, this is the same thing showing what a vertical does in terms of its directivity. It's omnidirectional. Okay, next one. Okay, yes.
So if you have a dipole antenna, it's only transmitting this.
Okay. That is a really, really good question, and you can easily be misled. Let me show you how this works. What we described of it transmitting only in that donut is if you are in what is called free space. And free space is somewhere between here and the moon or here in the sun, okay? Because this is what happens. I'm going to look at the end of the dipole antenna. So this is the end of the wire. Wire's going this way. Underneath it, unfortunately, I have this thing called the earth, right? Now, a radio wave leaves this and it's being radiated in all directions. But the one that leaves right here comes down and it hits the earth and it is reflected off. Okay? So there is some point out here in space, this wave is going out here in space. There are places in space where this wave will add with the reflected wave. And if it adds with it, does that make it bigger? And there are also places in space where it will what? Subtract. And that's a fixed spot. So what happens is there is one of the lobes will come out here like this. Right here. You'll have some going up there, but you'll have major lobes coming out this way. An example of this, we have a ham here locally, K7JH, John Hunter, sharp guy. John and I were kids at the same time, and we got trying to chase DX. And one thing that we wanted to achieve is that we wanted to get what was called DXC, WAZ. And the last zone in the world that I needed was in Mongolia. The last zone he needed in the world was Mongolia. And so early one morning, I'm tuning around and I hear this Mongolian. And I jump on him, grab him. And then I call John, not even up, say, John, there's a Mongolia on 14, da da da. And so John runs downstairs, works Mongolia. Well, we both got cards from Mongolia. His came a week before mine. And so we both have the same award, but he has one number. No more nice guy. Okay. But the thing about John, his antenna was 100 feet in the air. My antenna was 50 feet in the air. Because his antenna was higher, this angle was much lower than mine. And he would hear, and the other stations on the other end would hear him 20 to 30 minutes before they would hear me. And the whole difference was he was higher in the air. Therefore, when the wave came out, hit, bounced, the place at which it added was lower to the horizon. So therefore, he had gain over me. Does that make sense? Okay, like I say, no more nice guy, because it cost me. Okay, what do we need to build these antennas? Well, you need some wire. That to be fancy? No. When you first start, go out and buy some speaker wire. And it gives you 100 feet of speaker wire, or even 50 feet. You tear it in half, now you got 100 feet. Okay? Works perfect. Half of my little antennas that I take out in the mountains are made out of speaker wire. Okay, you need some cable. Now, I said this, being a vertical, has what impedance? 50 ohm. If it were a dipole, what would it be? 72 ohm. I have right here several kinds of coax. This is called coax. Why is it called coax? Well, I see that I have a center conductor right here, right? You see that center conductor? Then I have insulation, and then I have another conductor out here. What are their shape? Round, right? They have a center point right there, and since they have the same center point, therefore they are called coaxial. Does that make sense? Called coaxial because you have the same center point. Now, this is 50 ohm coax. Okay? This is 50 ohm coax. Okay? This is 50 ohm coax. Let's see. This is 50 ohm coax. What's the difference between them? Size. Okay? Tell me what you think this might do that this won't do. Okay, better shielding. Also, what did you say? Okay, you can run megawatts on some of this stuff. What happens if you put 100 watts on this? It fries, but it will still work. And for instance, right here, this is my 50 ohm coax that I take out into the mountain. Why don't I have to have great big coax? Because I'm real low power. Okay, the maximum power I run on this is sometimes I'll cheat and go up to 50, but most of the time, this little radio here, 4 watts. If the battery's running down 3 or 2 watts. Okay, but I don't need to carry this kind of stuff. Okay, now, an interesting thing though is I reach over here in my little stack, and here's a piece of coax. What do you think it is? Wrong. Okay, I gotcha. This is 75 ohm coax. Okay, now what's the difference? And I lost my pen again. Okay, the difference is the ratio of the diameter and what's inside the wire. I'm going to put a formula up here. Don't let it it says ZO, and that means it's characteristic impedance. In this case, 75 ohms, in this case, 50 ohms, is equal to 138 log of big D over little d divided by the square root of the dielectric constant. Now, that's not as complex. Could you measure the inside diameter, size of that wire? Could you measure the inside of that one? Yeah, and inside this one, what is that that's inside there? Okay, that's foam, isn't it?
Yeah, oh, here.
Yeah, that's foam. Well, it turns out that foam has a dielectric constant of 0.8, and all that means is that a radio wave travels through this at 80% of the speed of light. Now, if I find one here, this one right here, this one is very stiff, hard to bend. The inside of this one is made out of polyethylene plastic, and a radio wave travels through it at 0.66, another 66% of the speed of light. Well, those things figure into the equation here. So you can't just pick up a piece of wire. You need to know what you're looking at. You need to know what its inside diameter is, outside diameter, and you also need to know what is in between. Okay? For instance, this one right here, that is solid polyethylene. That's 52 ohm coax. Now, in practice, you would use the 75 ohm coax to get best results on a dipole. You would use 52 ohms to get best results on a vertical. Now, don't I don't want you to think that that's a dyed-in-the-wool thing, because we said that the center impedance of the dipole right here was equal to 72 ohms, right? Well, as you move that thing up and down above the ground, that is what it would be if it were out in free space. Okay? So as you move them up and down, for instance, I use what's called an inverted V a lot. That means I have a pole, here's the insulator, here's one leg of the antenna, here's the other leg of the antenna. As I drop the legs down, the impedance drops, and it comes very close to 52 ohms. Okay? If I bring it up, it comes very close to 72 ohms. In practice, most of the coax that is used in radio, in ham radio, is 52 ohm. That's the one that's used more than anything else. Does that make sense? Okay. No. If that is an excellent question. If this is the correct length, that means the antenna is what? Resonant, right? Okay. Well, if it's resonance, the wave comes up here, it oscillates. How much is reflected back? Nothing. Okay? If it's the right length, the antenna works the right way, nothing is reflected back. Also, if I take a piece of wire, for instance, this antenna I didn't show you yet. This is what is called a Quaggy antenna. A Quaggy antenna. Now you got the Yagi part of it, right? Okay. This antenna back here, forget all that for a minute. This is a full wavelength of wire on 450 megacycles. This is a full wavelength of wire on 450 megacycles. I put power in here. This oscillates because it's a full wavelength is twice a wavelength, right? And so everything works in multiples as you go up. So this one radiates, comes back, hits this one, it breaks into oscillation. Its distance is such that it cancels anything going that way. So this is called a what? Reflector. Okay? Then somebody got really cute. They said, well, this is a director, which directs it. This is another director, another director, another director, another director, another director. So the wave from this hits this, it oscillates. The wave leaves there, oscillates, hits this one. Both waves then hit this one and oscillate. All of those three then hit this one and it oscillates. And what's happening to my beam width on this thing? It's getting narrower and narrow, and what's happening to my gain? It's going up. Does that make sense? By the way, what does it cost to build that? Number 12 house wire, 2 pieces of plastic, a piece of wood, and 3, well, let's see, and pieces of short welding rod. Yep. Yeah. Okay. Now let's see. Let's go back now.
You've got it so you can hook it onto a pole. So does that pole mess with your oscillation?
Yes, the pole, I hook it onto a pole, and that pole, by the way, the magnetic fields and electric fields are in this plane, right? The pole is in this plane, does not interact with it. Okay, theoretically. Okay. One other thing I need to tell you. One of your questions deals with PL259s. And that is a kind of connector. This is a PL259. This is what's used on most radios, okay? But as you go up in frequency, it becomes trickier to get things to work exactly the way that you want. because as you go up in frequency, things just happen. So there's a special kind of connector, and this is called an N fitting. And this is what you use for very high frequency stuff. So I'll pass that around, look at it. That is an N fitting. And when they ask you the question there about if you're operating at 400 megacycles, what kind of fitting are you going to use? That's the kind of fitting you're going to use. Okay? Well, it just makes it so that it maintains the relationship of center conductor, so on and so forth, so that the ratios are still 52 ohms. Okay? So that's an N fitting. This antenna is on 450 megacycles, so guess what kind of fitting is on here? That's an N fitting. By the way, they are expensive. Okay? And here is an N fitting on this little dandy here. So what frequency do you think this was used for? Was it low frequency stuff? No, used for something way up there. And by the way, that little fitting right there, all by itself, is over $100. Is this something that ham radio operators generally use? No. Well, I've met a few that would. Okay. Okay. Now let's go back to the book here just a second and see what kind of progress we've made. Okay, do you know what vertical polarization and horizontal polarization is? What is it that determines what the polarization is? Okay, upper sideways, okay. The electric fields, and the electric fields are always parallel to the wire, right? Okay, do you understand the concept of gain? Gain simply means that you don't put any more power out, but you simply concentrate it down, okay? Common portable mobile antennas, okay? Common portable mobile antennas, this is what you put on top of your mobile, right? Okay, another portable one right here is this little doodad. Right there, that is what's called a 5/8 wave antenna. Its counterpart is this right here, which is called a rubber ducky. Okay, now the rubber ducky, which one's the longer? This is called a 5/8 wave. By the way, this is 2-band 5/8 wave. This is just single band antenna. But this one being longer has a tendency to make it so that the waves are squashed. This one, on the other hand, which one has the most gain? This one, okay? All this one actually is, if you look at it close enough, you can just see they've wrapped wire around there like that. Yeah. And these things are not effective. They are not effective. Rubber duckies are not effective. Buy a few bucks and get yourself 5/8 wave, okay? Now, one of your other questions is, why wouldn't you want to use one of these things inside your car? Okay, the car is, a lot of it is metal, right? And so you're in a Faraday cage. You got it exactly. So if you want to use your handy-talkie in the car with the antenna, you simply open the door and stand out on the running board. Okay, so it's very important that you have some kind of an antenna outside there, okay? So the rubber ducky, that's one of your questions about why isn't that, why, okay? You know about horizontal vertical polarization. Do you know what the concept of resonance is? And you remember we said the resonant means the antenna is the right length, right? Now, as I go up in frequency, what happens to the wavelength? Gets shorter. So one of the questions, for instance, they ask you this question. If you have an antenna and you want to lower your frequency, what have you got to do with the length of the antenna? Got to make it longer. Yeah.
That's why it sucks.
That's right. That's right. Okay, does that make sense? So that is the concept of resonance, and that's why you have to make the antennas the right length and so on and so forth.
You can check that with an SW.
Yeah, the SWR meter. Let me just quickly explain what that is. Yeah. Well, you can let the, I'm running out of time. I'm running out of time. Okay. Okay, here's what happens. I have an antenna right here, and I have the transmission line. I put a little meter right here, and this little meter measures the power going to the antenna like that. Okay? It comes here to the transmitter and the receiver. Now, if the antenna is the right length, somebody wants to know if I need insurance on my car. Let's see. If the antenna, if the power comes up here and this is the right length, what happens? Everything goes out. And so the meter simply reads forward power. Forward power. But all of a sudden I change the transmitter frequency, and now I've lowered the frequency. That means the antenna is what? It's too short, right? So now this power comes up here, but when it hits this, some of it comes back this way. And as it comes back this way, this meter now measures the reverse power. Okay? And there's a little mathematical formula that says so much voltage going this way, so much voltage coming back, the ratio of those voltages, and it's a little mathematical formula I won't give you. Simply tells you how well your antenna is working or if it's a resonance. This is called an SWR meter, standing wave meter. And I wish I had time to explain it all to you because it's a beautiful concept. Not that hard to understand, but we're out of time. Okay, now, does that mean I can't possibly use this antenna on other frequencies? Not as efficient, but I can cheat. And I can come over here and I put another little thing in here, which is called a matchbox. What do they call it? Transmatch, is that what they call it? What do they call it? It's in your questions. Anyway, it's called a tuner. Tuner is what they call it, okay? And what the tuner does, it doesn't help the antenna at all. If the antenna is bad, it's still going to be bad. But it tunes out the reflection coming back here and makes the transmitter think that the antenna is working. Okay? So now I can, that's good, because what happens on modern transmitters is if there's power coming back, to save itself, the transmitter reduces its power. Okay? And so you lose both ways. But if I put this thing in here called a tuner, now I can adjust it so that it takes all the mismatch out, at least makes the transmitter and receiver think that the mismatch is tuned out. Now the transmitter still sends its full power, still reflecting back power, but at least you're getting a little more out. Does that make sense? So that's called a tuner. Okay. So you know what a dipole antenna is? That covers that. Now let's go to the last section, overhead. And it says types of feed lines. Okay? And there are a couple things I missed. These are both 50 ohm lines. If I were to put power into this one, into 100 feet of it, and I were to put power into this one, 100 feet of it, which one would have the most power get to the other end? The big one. So the bigger the transmission line, the better. Okay. The other thing was SWR concept. You got tuner, we just talked about, connectors, and the need to weatherproof. Okay. what do you think happens if I get water inside this? All of a sudden, the characteristic impedance, the formula, ZO equals, it's gone, okay? And so you get loss and reflection, so on and so forth. Okay, let's see, was there anything else? Okay, are there questions that you have? Now, my approach to this tonight is it's fine to go through and memorize the answers. But if you understand the concepts, even if you hadn't read that, you should be able to come up with the right answers. Okay? So you've just had a elementary, very, very non-mathematical elementary presentation on radio antennas. And you're going to fall in love with them because they're fun to play with. When we were in New Zealand, you know, there were no mountains or anything. And my wife would say, how in the world do you keep track of where you are? And I'd say, well, I just saw that guy's Yagi over there. That guy's got a quad. Oh, down here, there's a broadcast station and they're using this kind of antenna. And so on my way, I found my way around the island was from antenna to antenna. Okay, because it is a fascinating thing. You can do great things with it and just have a ball. And they're inexpensive, fun to build. And if you get going and you need an antenna and you need parts for it, hey, I'm an old guy and you would not believe what I have in the way of a junk box. And you need feed line or wire, for heaven's sakes, call me. Because my wife would be delighted if it went out the door. Okay.
Don't worry about the wiring around.
Yeah. Oh, she already found that with the rototiller. Okay, thanks, guys. Really.
Thank you.
That was whirlwind clap.